Welcome to the third episode in the first part of our series, Adventures in Op-Amps. In the previous episodes, we saw that negative feedback may be a viable method that can prevent clipping of the output signal due to the high gain of the op-amps. In this third episode, we will explore how negative feedback works, starting with a couple of thought experiments that will give us an intuitive feel of the mechanism that makes negative feedback so effective. Let's go back to our original amplifier configuration that, as we saw in the previous episodes, did not work so well. Let's put 0 volts on the positive terminal of the op-amp, and observing that the negative terminal is connected to ground, which is 0 volts also, then the difference between the two terminals will be 0, and the output voltage will therefore be 0. Now let's remove the ground connection and very quickly insert the negative feedback short circuit that we saw in the last episode between the output and the negative terminal. The output was previously at 0 volts, and since the short circuit feedback conveys that value to the input, then the input to the negative terminal will remain at 0 volts. With both inputs at 0 volt, the difference between them remains 0, and even if the value of the gain is very high, the output voltage will remain at 0 volts. That 0 volts coming out of the output is again fed back into the input, which keeps the amplifier stable at the state, with the output showing the same value as we applied on the positive terminal of the op-amp. If we were to place the operating point of this op-amp on the input-output curve of the op-amp, we would have 0 for the x-axis and 0 for the y-coordinate, which would place us exactly at the origin of the input-output curve as denoted by the green cross. Notice how the feedback keeps the output locked at 0 volts, which is exactly the same voltage as the input. Also notice that the feedback places the op-amp in its linear region. Now let's see what happens when we start increasing the input voltage on the positive input terminal. Starting with the previous condition, where both inputs were at 0 volts and the output was also at 0, now let's start to raise the voltage on the positive terminal from 0 volts towards a very modest 1 millivolt and see how the system reacts. Naturally, a rising voltage on the positive input will cause the output voltage, Vout, to start rising from its previous value of 0 volts to a new higher level. Eventually, it should settle at a new value that is proportional to the difference between the two input terminals. But what is the difference in voltage between the two input terminals? A negative feedback connection will make the negative input equal to the value of the output voltage. So as the output voltage rises, the voltage on the negative input terminal will also rise. That rising voltage on the negative input terminal means that the difference in voltage between the two input terminals gets smaller as the output voltage increases. This puts a limit on how high the output voltage can go, and that is the essence of negative feedback. The output voltage will not rise to a very high value because as the output voltage increases, negative feedback kicks in and limits its final value. The question now becomes, at what value will Vout settle? Would it be much higher than the 1 millivolt, or will it be somewhere closer? We can find out the exact end value of the output voltage by solving two simultaneous equations which describe the behavior of this system. The first equation is the feedback equation, that is, that the voltage on the negative input is equal to the output voltage. The second equation is the one that describes the input-output relationship of the op-amp. But this op-amp equation is problematic because we do not know what region the op-amp is operating in. Will it be in the linear region or in the saturation region? We need to find out which region the op-amp is in to solve these two equations. And to figure out which region the op-amp is working in, let's do a few quick thought experiments. Because we do not know the final voltage of Vout, let's start off in the first thought of experiment by guessing that the Vout is somewhat higher than the input voltage of 1 millivolt. After all, the op-amp is supposed to amplify the input. So let's guess that Vout is at 3 millivolts. If there is no feedback, then this may be a feasible situation. But due to the feedback mechanism, that 3 millivolt output voltage will show up at the negative input terminal. And with 1 millivolt on the positive input terminal and 3 millivolts on the negative input terminal, the difference between the two terminals is minus 2 millivolts. If that difference between the two input voltages is negative, then Vout also has to be negative. That means that the internal working of the op-amp will now start changing the value of Vout, trying to push it downwards towards some negative voltage value. But then things get really interesting, because as Vout decreases from its 3 millivolt values towards some ultimate target negative voltage value, the feedback connection will force the voltage on the negative input terminal to also decrease. That means that as Vout decreases, the difference between the two input voltages will get smaller and smaller. What will happen next when the output voltage drops just below 1 millivolt? That's the 1 millivolt that we applied on the positive input terminal. Time for another thought experiment. In our next thought experiment, let's think about the situation where Vout dropped below the value of the voltage on the positive input terminal and is now sitting at 0.9 millivolts. Because of the feedback mechanism, the voltage on the negative input terminal will also be at 0.9 millivolts. When we subtract that 0.9 millivolts from the 1 millivolt on the positive input terminal, then we end up with a positive value of 0.1 millivolts right before the gain stage of the op-amp. A positive value for the difference between the two input terminals means that Vout has to have a positive value. Not only does it have to have a positive value, but because of the very large gain, which we assume to be around 100,000, the target for that Vout should be the difference times the gain, which would be a target of about 10 volts. That is well within the supply voltage limits, and so seems like a plausible target. Of course, as Vout starts to rise towards a target of 10 volts, then the voltage difference between the two input terminals will get smaller. And because of the very large gain of the op-amp, for every small decrease in the difference between the two input voltages, there will be a large drop in the target voltage for Vout. For example, when Vout reaches 0.99 millivolt, the difference between the input voltages becomes 0.01 millivolt, and the target voltage drops from that 10 volts to 1 volt. All this thinking gets us wondering about how far the rising output voltage will go. Let's dive a little bit deeper into this thought experiment in search of the answer. As Vout keeps rising and getting closer to the input voltage of 1 millivolts, it will eventually reach 0.999 millivolts. And due to the feedback, that will become the new level at the negative input terminal. The difference between the positive and negative terminals now drops to only 0.001 millivolts. Multiplying that by 100,000 again, the target for the output voltage is now lowered from 1 volt to only 100 millivolts. Think about that for a second. We have a situation here where the difference between the two input terminals is 0.1%. Yet because of the very high gain of the op-amp and the feedback mechanism, Vout is still rising and will continue to make the difference between the voltages between the two input terminals very small, much smaller than the already achieved 0.1%. So we can expect the voltage on the input negative terminal to get even closer to the voltage that we placed on the positive input terminal. This behavior, where the feedback circuit and the high gain working together force the voltage of the negative input terminal to get closer and closer to the voltage on the positive input terminal, is often called the virtual short circuit between the two input terminals. We use the term virtual because there is no physical connection between the two input terminals that is forcing them to have approximately the same voltage level. Yet the feedback configuration and the high gain of the op-amp are working together to bring the voltage of the negative input terminal ever so nearer to the voltage that we placed on the positive input terminal. To find out the ultimate value for Vout for this configuration of the op-amp and the feedback circuit, we can continue to assume an ever-rising value for Vout and redo the calculations to see if we have reached a stable point. Or better still, we can go back to the two equations that will tell us where Vout will converge. The last time we saw these two equations, a few slides ago, we did not know which region the op-amp will be working in. But thanks to the two thought experiments that we just did, we can now answer that question. Let's now pay close attention to the clues that were revealed by our two thought experiments. The first thought experiment told us that having Vout larger than the input voltage is not a feasible operating point for this particular op-amp configuration, because that will result in the target output voltage being a negative number, which will then push the voltage on the negative input terminal down below the input voltage. But whenever that happens and the voltage on the negative input terminal gets below the voltage on the positive input terminal, then the conclusions of the second thought experiments kick in, and they tell us that the output voltage will head upwards, getting ever so closer to the value of the input voltage. And because of the feedback connection, the now rising output voltage appears on the negative input terminal. And yet, the output voltage can never exceed the input voltage of the positive input terminal, as we saw in the result from our first thought experiment. With this summary in mind, we can now look at the input-output curve of the op-amp and determine in which region it will operate. Starting with the feedback equation that forces the negative input terminal to be the same voltage as the output terminal, we know from the first thought experiment that for this circuit configuration, the feedback mechanism ensures that the output voltage is never higher than the input voltage, which means that the voltage on the negative input terminal will always be lower than the input voltage on the positive input terminal. That means that the difference between the two input voltages will always be positive. Therefore, we can eliminate the entire left side of the input-output curve as a possible operating point. So now, let's see where on the right side of the graph will the op-amp be operating. So now the second thought experiment comes into play and tells us that because of the feedback and the high gain of the op-amp, Vout will move closer to the input voltage, and because of the feedback, the negative input terminal will also move in tandem, also getting very close to the value of the positive input terminal. In our second thought experiment, the difference between them had already gotten to 0.1% and was still heading lower and lower. And not only is the difference very small, it's also positive, as we discovered from the very first thought experiment. This means that the op-amp must be operating very close to the origin of the input-output curve, but on the positive side on the x-axis. So let's put the green X mark in the general area of the operation. So all this thinking leads us to the conclusion that the op-amp is operating in the linear region, and therefore we can now solve the pair of equations that will reveal the exact relationship between Vout and the input voltage for this amplifier. So we start off with our feedback and op-amp equations, but we now know that the op-amp is in the linear region, so we can use the op-amp linear region equation instead. Now applying the feedback equation to eliminate the negative input terminal term inside the op-amp linear region equation, we solve for Vout as a function of the input voltage to get this very simple equation. This equation tells us that as long as the gain factor is positive, which it always will be in op-amps, the output voltage will always be just a tiny fraction lower than the input voltage. We can validate this by plugging in the typical gain value of 100,000 into the equation to see how close the output voltage is to the input voltage. And the value looks very close to 1. And because of the feedback equation, the voltage on the negative input terminal will also be very close to the input voltage. If you recall, at the start of this journey, we wanted to create on the negative input terminal a new version of the faint input signal that was just a fraction smaller than the signal on the positive input terminal, so that we would not get any clipping on the amplifier output. From this last equation, it seems that we have accomplished this goal on the negative input terminal through the use of negative feedback. However, a closer look at the equation for the output voltage reveals that we did not get any amplification of the input voltage. The output voltage will just closely follow the value of the input voltage, and that is why this configuration is called a voltage follower. In practical electronics, there are many situations where such a configuration of the op-amp is actually quite useful, and we will discuss these in part 3 of our series. But for now, we need to solve the problem that our very first amplifier does not seem to amplify the input signal. And that is exactly what we will do in the 4th and final episode of part 1 in our adventure in op-amps. See you there.